Okay, Paula, if you are ready, we may start.
Okay, sure, yeah.
Okay, very good. Welcome everybody for this last lecture of the day. And it's my great pleasure to introduce Paula Burkhardt from UC Berkeley. And she will talk about pointwise lower scalar curvature bounds for C0 metrics via regularizing Ricci flow. Thank you for that.
Okay. Yeah, great. Thank you for the introduction and thank you for having me. It's a pleasure to be here virtually. All right. I'm going to start with this theorem, which is due to Gromov, and it says the following. Let M be a smooth manifold, then kappa from M to R be a continuous function. And suppose that we're in the following situation. So suppose we have a sequence of Riemannian metrics Gi that converge uniformly to some limiting Riemannian metric G. And suppose also that for every Gi in the sequence, the scalar curvature, so I use R to denote scalar curvature, the scalar curvature of each of the Gi at X is bounded below by kappa of X for all X in M. Okay, so we are assuming this pointwise lower scalar curvature bound on every metric in the sequence. And then so suppose that we also happen to know that this limit is C2. Okay, so these are C2 metrics, they're converging uniformly. And then we're assuming that somehow we happen to know that this limiting Riemannian metric G is also C2. And if that is the case, then the punchline is that the scalar curvature of this limiting metric G is also bounded below by kappa. So in other words, pointwise lower scalar curvature bounds are preserved under uniform convergence. Okay, so somehow this is actually like a rather surprising result. You know, here we only have uniform convergence, and so we wouldn't really expect to be able to say much about the scalar curvature of the limiting metric, and yet somehow these pointwise lower scalar curvature bounds are preserved nonetheless. So if we wanted to prove this theorem, we could proceed in one of two ways. The first method is due to Gromov, and so basically what he does is he notices that having a pointwise lower scalar curvature bound can kind of be understood as a C0 condition. And since you can understand it as a C0 condition, it is, you know, the C0 condition is going to be preserved under C0 convergence. And so, you know, another way of saying that is that basically what he does is he creates this sort of generalized notion of what it means to have a lower scalar curvature bound that is well defined for C0 metrics. And crucially, it is stable under C0 convergence. And of course, it agrees with the usual notion of what it means to have a lower scalar curvature bound if we have a C0 metric, which is actually C2. Okay. So if we had sort of a generalized notion like this one created by Gromov, then the way that you could prove this theorem is the following. So my Gi satisfies some pointwise lower scalar curvature bound in the usual like classical sense. And so they also satisfy a lower scalar curvature bound in this sort of generalized C0 sense. All right, but then this generalized C0 definition is stable under C0 convergence. So the limiting metric G is also going to satisfy this pointwise lower scalar curvature bound in the C0 sense. But then we happen to know that this limiting metric is C2. So because it satisfies this sort of generalized C0 lower scalar curvature bound, it also is going to satisfy the classical lower scalar curvature bound. All right. And so, you know, I'm not an expert on Gromov's definition, and I'm not really going to talk about it very much for the, you know, throughout this talk. But basically, his definition has to do with the non-existence of certain types of polyhedra. So, okay, maybe I will just write like polyhedral definition. All right, so that is one way that you could prove this theorem is by somehow, you know, understanding lower scalar curvature bounds as this C0 quantity and creating this like generalized notion of what it means to have a lower scalar curvature bound. Another way that you could prove this theorem is due to Bamler, and this method is to use the Ricci flow. Okay, so let me just remind you, what is the Ricci flow? The Ricci flow is an evolution equation for Riemannian metrics on a manifold. It's this evolution equation. I always call my Ricci flows tilde GT. Okay, and so the Ricci flow equation is the time derivative of tilde gt is equal to -2 times the Ricci curvature of tilde gt. And then we can prescribe some initial data. All right. And so, the reason that you might sort of guess that Ricci flow is relevant to this theorem is that there's this nice sort of classical fact about scalar curvature under the Ricci flow, which is that uniform lower scalar curvature bounds are preserved by the Ricci flow. So what I mean is that if my initial metric G0 has scalar curvature bounded below by some uniform constant kappa 0, then for all positive times t for which the Ricci flow is defined, the scalar curvature of each time slice tilde gt is also going to be bounded below by kappa 0. Okay, and so sort of inspired by this fact, if we wanted to prove this theorem using the Ricci flow, we could argue sort of in the following way. I'm actually kind of lying here, but maybe this will just give you a sense of the argument. So here is the idea. The idea is that we have this sequence of metrics that are converging uniformly to some metric. And so what we could do is we could run the flow starting from each metric in the sequence. And then we could run the flow starting from the limiting metric. And then somehow okay, as I said, I'm lying a little bit, so that somehow the flow will turn the uniform convergence of the initial data into locally smooth convergence of the flows for positive times. So this is for t strictly greater than 0. And so then we could prove this theorem, at least in the case of uniform lower bounds, we could prove the theorem as follows. So the GI satisfies some lower bound on the scalar curvature. And then if we're just in the case of uniform lower bounds, those uniform lower bounds are preserved by the flow. So the GI of t satisfy the same lower scalar curvature bound. But then by this locally smooth convergence, the limiting flow is also going to satisfy that lower scalar curvature bound. And so we could just let t go to 0 and find that g satisfies the same lower scalar curvature bound. Of course, as I said, I kind of lied a lot during this explanation. And one of the main things that I lied about is that, this argument that I just said only works in the case of uniform lower scalar curvature bounds, because we know that uniform lower scalar curvature bounds are preserved by the Ricci flow. It is not necessarily the case that pointwise lower scalar curvature bounds are preserved by the Ricci flow. So if you wanted to prove the full version of this theorem using the Ricci flow, you need to figure out some way of localizing the argument that I just said, and this is a non-trivial thing to do, but this is what Bamler does in his proof. Okay. So we have these two methods of proving this theorem of Gromov. The first.
Excuse me, Paula, there is a question in the room. So.
Oh, okay.
Yeah. M is a closed manifold or open manifold or just a compact manifold with boundary?
So I haven't specified. I'm actually going to always take M to be closed, but in this case, I think M is some smooth manifold, probably without boundary. I don't think there are other conditions on M.
Thank you.
Mm-hmm. Okay, so we have these two different methods of proving this theorem. One is to sort of understand lower scalar curvature bounds as a C0 quantity and have this sort of C0 definition of what it means to have a lower scalar curvature bound. And the other method is to use this Ricci flow argument. And a priori, these two methods, don't appear to have very much to do with one another. But the fact that we have these two proofs of the same theorem leads us to ask whether there is some underlying connection between the techniques that are used in both of them. Okay, and so that is sort of what I'm interested in examining throughout this talk. And so sort of our motivating question is the following: can Gromov's C0 definition of lower scalar curvature bounds be reformulated in terms of Ricci flow? Or in other words, is there some sort of C0 definition of lower scalar curvature bounds using Ricci flow that is equivalent to Gromov's polyhedron formulation? Okay. So I don't know the answer to this question, but one reasonable first step towards answering this question would be to first try to use Ricci flow to come up with a reasonable definition of lower scalar curvature bounds for C0 metrics, and make sure that such a definition sort of behaves the way that you want it to. And then hopefully once you have such a definition, then you can check whether or not it's equivalent to Gromov's. Okay, and so that's the goal for this talk. The goal, so yes, to reiterate, the goal for this talk is to develop a reasonable pointwise notion of a lower scalar curvature bound for C0 metrics that uses the Ricci flow. Okay, just gonna have some water. Okay, and so, if we are going to create such a sort of reasonable C0 definition, of lower scalar curvature bounds, there are certain items that we would like this definition to satisfy. So first of all, we would like this definition to be stable under greater than second order perturbation of the metric. So what I mean is that if G prime and G prime prime are two C0 metrics such that their difference in a neighborhood of some point x naught is bounded by some polynomial of degrees strictly greater than 2 in the distance to x naught, then G prime should have scalar curvature bounded below by kappa at x naught in this sort of generalized C0 sense, if and only if the same is true for G prime prime. Okay, so this condition looks a little bit complicated, but it's actually very natural. And to see why that is, you can just think of like analytic functions on Rn. So, if you have this condition for two analytic functions on Rn, that means that if you look at the, the Taylor series for both of those functions centered at x naught, this means that sorry, there was a noise outside. This means that the 0 first and second order derivatives of the two functions had to all be equal at x naught. So somehow this is a C0 condition, which in the case of smooth metrics would imply that the scalar curvatures are equal. All right, so yeah, so from now on, I'm going to refer to this item as stability of the definition under greater than second order perturbation of the metric. Okay. And then the second thing that I would like to be true is that I would like to continue to have this sort of nice like classical property about uniform lower scalar curvature bounds. I still want to have that in my C0 definition. So what I mean is that if G is a C0 metric on a closed manifold M that satisfies some uniform lower scalar curvature bound in the generalized sense, and tilde GT is a Ricci flow starting from G. Okay, this is in quotes because I have to explain what this means. But if I somehow have a Ricci flow starting from this C0 metric, then I would like it to be the case that the scalar curvature of each time slice of the flow, so each tilde GT for which the flow is defined, satisfies the same uniform lower scalar curvature bound. Okay, and so I will refer to this as preservation of global lower scalar curvature bounds under the flow. And then finally, of course, I want my generalized C0 definition to agree with the usual notion of a pointwise lower scalar curvature bound if I have a C0 metric which happens to be C2. Okay, so as I mentioned, the goal was to use Ricci flow to define what it means to have a lower scalar curvature bound for C0 metrics. And in order to do that, I probably need to explain to you what it actually means to have a Ricci flow associated to a C0 metric. Of course, if you were in the case of a smooth metric, the Ricci flow for the smooth metric would just be a solution to the Ricci flow equation that converged uniformly to the initial data as t goes to 0, and also all the derivatives would converge uniformly to the derivatives of the initial data. Obviously, this doesn't make sense if you only have a C0 metric because the C0 metric is not going to have any derivatives, but you could at least hope that you can find a solution to the Ricci flow equation that converges uniformly to the initial data as t goes to 0. Or I guess, sorry, I keep saying like converges uniformly. I'm being a little sloppy about that because for the rest of the talk, I'm just going to consider closed manifolds. But in the case of manifolds that are not closed, I guess you would have locally uniform convergence. Okay, anyway, so yes, henceforth, I will take M to be closed. The compactness is not essential for everything that I will do, but it helps with some things. Okay, and so yes, now what I'm going to tell you is basically that you can find a Ricci flow that is associated to C0 initial data, and it doesn't exactly converge uniformly to the initial data as t goes to 0, but it will converge uniformly to the initial data modulo push forward by a family of diffeomorphisms. Okay, and so here is the result that explains what it means to have a Ricci flow starting from C0 initial data. All right, so I will read it now. Let M be closed and G be a C0 metric on M. Then there exists a time-dependent family of smooth metrics tilde GT for t in this positive time interval, and there exists a continuous surjection chi from M to M such that the following are true. So first of all, the family of metrics tilde GT solves the Ricci flow equation. And also there exists a smooth family of diffeomorphisms chi t defined on the same positive time interval such that the chi t converge uniformly to chi as t goes to 0, and the push forward of the Ricci flow by the chi t converges uniformly to this C0 metric G as t goes to 0. Okay. So yeah, I mean, this looks a little bit complicated. I should just mention, so this push forward, this family, I guess, of metrics that converges uniformly to the C0 metric G, I mean, this, maybe some of you who are familiar with this will recognize this as, another another family of metrics that satisfies a nice sort of flow equation, namely this is the Ricci de Turck flow. Okay, and yeah, I'll talk a little bit more about this later. And then, yeah, I should also mention, so here we have this continuous surjection chi. You know, I don't know of a counterexample that says that it's not always possible to make chi be a homeomorphism. I think, you know, maybe it possibly should be, maybe there should be such counterexamples, but yeah, I don't have one off the top of my head. Okay. So we say that the pair tilde GT, so this is the family, which is the Ricci flow, together with this continuous surjection chi is a regularizing Ricci flow for G. And the reason I use the word regularizing here is that this family tilde GT is smooth, you know, these are all smooth metrics, despite the fact that the initial data G is only C0, it's not smooth. Okay. A couple more remarks. So this smooth family of diffeomorphisms, you know, is reasonably well behaved in the sense that it perturbs points like square root of t. And then we have uniqueness of the regularizing Ricci flows up to isometry. So what I mean is if tilde GT prime chi prime is another regularizing Ricci flow for the C0 metric G, then there exists a diffeomorphism alpha such that the pullback of tilde GT by alpha is equal to tilde GT prime, and chi precomposed with alpha is equal to chi prime. Okay, so yeah, this looks a little bit complicated, but in practice, it's actually not so hard to work with. Anyway, and so now I've told you what it means to have a Ricci flow starting from C0 initial data. And so if I want to define what it means for C0, my C0 initial data to have a pointwise lower scalar curvature bound, you know, this is how I'm going to reason. So, you know, I have this Ricci flow, and despite the fact that the initial data is not smooth, this regularizing Ricci flow is smooth for positive times. So if I want to know whether my initial data satisfies some kind of lower scalar curvature bound at a point, what I should do is run the regularizing Ricci flow and then check whether, you know, as t goes to 0 for small positive times, the flow satisfies a similar lower scalar curvature bound in the, you know, in a nearby region. Okay, and so that is how I'm going to define what it means for the C0 initial data to have a lower scalar curvature bound. Okay, and so here is the definition. Excuse me. Okay, so I'm going to read it and then I'll sort of break it down. So here's the definition. Let M be closed and G be a C0 metric on M. For beta between 0 and 1/2, we say that G has scalar curvature bounded below by kappa at X in the beta weak sense. If there exists tilde GT chi, a regularizing Ricci flow for G, and there exists some point Y in the pre-image of X under chi, such that the following expression is true. The infimum over all C greater than 0 of the lim inf as t goes to 0 of the infimum over the ball of radius c t to the beta about y of the scalar curvature of tilde g at time t if this whole thing is greater than or equal to kappa. All right, so this looks very complicated, but basically what I am doing is I'm, you know, considering the point X, and then I'm looking at the flow and I'm checking whether the flow has scalar curvature that looks as though it's going to be greater than or equal to kappa, sort of nearby the point X. Okay, so, you know, this infimum over all positive constants, this is not so important. You know, here what I'm doing is I'm letting t go to 0, so I want to check whether this condition holds for very small times because I'm trying to define what it means for the initial data to have a lower scalar curvature bound. And then here, rather than just considering, you know, the scalar curvature at the point X, I'm considering the scalar curvature in this neighborhood of size slightly larger than square root of t. But nonetheless, the size of this neighborhood goes to 0 as t goes to 0. Now, the reason that I'm interested in looking at the scalar curvature around y, where y was in the pre-image of X under chi, rather than looking at the scalar curvature around X, is that somehow, you know, the regularizing Ricci flow does not converge uniformly to the initial data. It just converges uniformly modulo this push forward by diffeomorphisms. So the reason we look at this point Y in the pre-image of X under chi rather than looking at X is to somehow account for this like twist by the family of diffeomorphisms. Okay. Okay, and so, you know, this definition depends on certain choices. For instance, chi was a surjection, but not necessarily a bijection. So there could potentially be multiple Y in this pre-image. And then also, as we saw, there are potentially multiple regularizing Ricci flows for any C0 piece of initial data. However, this definition is independent of those choices. So if it holds for one choice of y in the pre-image of x under chi and one choice of regularizing Ricci flow, then it will hold for all choices y in the pre-image of x under chi and all regularizing Ricci flows for g. Okay, this I already mentioned. All right, so yeah, so this is how I'm going to define what it means to have a C0, a lower scalar curvature bound for a C0 metric, and it's basically what I'm going to do is, as I said, run the Ricci flow and then check the scalar curvature of the Ricci flow sort of near that point. All right. And so just to remind you, there were certain items that I wanted this definition to satisfy. First of all, I wanted the definition to be stable under greater than second order perturbation of the metric. Second of all, I wanted uniform lower scalar curvature bounds to be preserved under the Ricci flow. And so here now, I did not specify when we first talked about this what I meant by a Ricci flow starting from C0 initial data, but now I can say, okay, what I mean by this is a regularizing Ricci flow. Okay, so I want uniform lower scalar curvature bounds to be preserved by the regularizing Ricci flow. And then finally, of course, I want my definition to agree with the usual notion for C2 metrics. Now, sorry, what was I going to say? Okay, so now if G is a C2 metric, then I could just take the regularizing Ricci flow to be the usual Ricci flow. And then this would just turn into some limit as time goes to 0 of the scalar curvature at x, which is equal to the scalar curvature of the initial metric at x. And so, it's fairly straightforward to see that this definition does indeed agree with the usual notion of a lower scalar curvature bound for C2 metrics. Okay, so this last item is not hard. So yeah, somehow the two difficult items that we have to deal with are these first two items, the stability of the definition under greater than second order perturbation of the metric and the preservation of uniform lower scalar curvature bounds. Okay, and so yes, next I'm going to tell you two, theorems that say that yes, indeed, these two items are true. Okay. So towards the first item, so in order to show that the definition is stable under greater than second order perturbation of the metric, I have this theorem which says the following: let M be closed and G prime and G prime prime be C0 metrics on M that agree to greater than second order around some point x naught. Then there exist regularizing Ricci flows tilde GT prime chi prime and tilde GT prime prime chi prime prime for G prime and G prime prime respectively, such that for beta in this interval, if C is some positive constant and T is sufficiently small, we have the following. Okay, so yes, and so the supremum over the ball of radius C, T to the beta around this point x naught, so x naught was the point around which they agreed to greater than second order, of the difference in the scalar curvatures of these two families of metrics. Recall that these were the families of metrics that uniformly approximate the C0 metrics. Okay, so these uniformly approximate the C0 metrics. So the difference in their scalar curvatures is bounded by C T to the omega, where omega is some small positive exponent. Okay, so what this is saying is that if you have two metrics, two C0 metrics that initially agree to greater than second order, then these families of smooth metrics that uniformly approximate them are going to have scalar curvatures that agree, in a ball of this size, right? So this is going to go to 0 as T goes to 0. Okay. Okay, and this looks a little bit technical, but if you sort of pay attention to what this says, and then I'll get back to that, and then I don't know, sort of untangle the definition, the sort of beta weak definition, it's not so hard to conclude from this theorem that this first item is indeed true. Okay, so yeah, somehow in order to show that this definition is stable under greater than second order perturbation of the metric, what we do is we, have this argument about the scalar curvatures of these two families of metrics that uniformly approximate the C0 initial data. Okay, let me just come back to this. So, this is just a remark. The way I've stated this theorem, G prime and G prime prime are two C0 metrics on the same manifold, but actually you should, or there is a version of this theorem where G prime and G prime prime are two metrics on different manifolds, and you can just find a coordinate chart for both in which the two metrics agree to greater than second order around the origin. Okay, so somehow this result does not depend on the topology of M. Okay, and so yes, as I said, this theorem sort of implies that this first item is true, that the definition is stable under greater than second order perturbation of the metric. And so now I want to address this second item. So our question is it the case that uniform lower scalar curvature bounds are preserved under the regularizing Ricci flow? And the next theorem says that the answer is yes. Okay, and so this theorem says the following: let M be closed and G be a C0 metric on M, and suppose there exists some beta between 0 and 1/2, such that the scalar curvature of G is bounded below by kappa naught in the beta weak sense everywhere in M. Then if tilde GT is any regularizing Ricci flow for G, the scalar curvature of every time slice tilde GT is also greater than or equal to kappa naught for all t greater than 0. I should say, for all t greater than 0 for which the flow is defined. So in other words, uniform lower scalar curvature bounds are indeed preserved under the regularizing Ricci flow. Okay, so yes, so all three of these items are satisfied, which is good news. Just one remark that I want to make as a consequence of this theorem is the following. So, okay, it follows that if G is a C0 metric that satisfies a uniform lower scalar curvature bound in the beta weak sense, then it automatically admits a uniform approximation by smooth metrics that satisfy the same uniform lower scalar curvature bound, right? And this is because the regularizing Ricci flow satisfies this uniform, it's a family of smooth metrics that satisfies this uniform lower scalar curvature bound. And after you push forward the regularizing Ricci flow by a family of diffeomorphisms, you'll get a smooth family satisfying some uniform lower scalar curvature bound that converges uniformly to G. Okay, so yes, so to recap, if G satisfies a uniform lower scalar curvature bound in the beta weak sense, then it automatically admits a uniform approximation by smooth metrics that satisfy the same uniform lower scalar curvature bound. And it follows, therefore, that it automatically satisfies Gromov's polyhedron definition. And the reason for that is that Gromov's definition applies to all smooth metrics with uniform lower scalar curvature bounds, and it's closed under C0 convergence. Okay, so corollary, in the case of uniform lower bounds, the beta weak definition implies Gromov's polyhedron definition. On the other hand, the converse I do not know. Okay, so this is a question I would like to know the answer to. In the case of uniform lower bounds, does Gromov's polyhedron definition imply that the beta weak definition holds? Okay, I should just mention, this characterization of the beta weak definition using like uniform approximation by smooth metrics that satisfy a lower scalar curvature bound, that only works in the case of uniform lower bounds. In the case of pointwise lower bounds, I don't think that there's an analogous statement. And so I don't think either direction of this question is known. All right, so in the pointwise case, this is another question I would like to know the answer to. In the pointwise case, do we have a lower scalar curvature bound at X in the beta weak sense, if and only if in the sense of Gromov? Okay, so are there questions so far? Okay. Yeah, so far I've told you sort of the, the definitions and the main results that I was interested in proving. And here are some, open questions that I would like to know the answers to. And I'm going to tell you a little bit also about how to prove some of these results. But I think I first want to go on a brief digression and talk a little bit about some consequences of thinking about scalar curvature using Ricci flow. Okay, and so here is a theorem, excuse me. Yeah, this theorem is a little bit convoluted sounding, but I will also draw a picture that I think will make it clearer. And so the theorem says the following: let G be a C0 metric on a closed manifold, which admits a uniform approximation by C0 metrics GI, such that for some beta between 0 and 1/2, GI has scalar curvature bounded below by kappa I in the beta weak sense everywhere on M, where kappa I is some sequence of numbers that converges to a limiting number kappa. Then G has scalar curvature bounded below by kappa in the beta weak sense as well. Okay, and so.
Excuse me, Paula, there's a question on the chat.
Oh, let me see. Okay. Gromov's polyhedron is his prism inequality. Yes, I guess so. So it's, or my understanding anyway, is that his polyhedron definition is that, a manifold has, or I guess a metric has non-negative scalar curvature if there does not exist a cube that such that all the, all the faces are mean convex and the dihedral angles are strictly acute. or at least that is if it has non-negative scalar curvature. And then for different values, different lower bounds, you take a product with a space form. Okay. All right, and so yeah, basically what this theorem is saying, it's a little bit convoluted, but basically what it is saying is that if you have some sequence gi, these are converging uniformly to some limiting C0 metric g, and then the scalar curvature of the gi are bounded below by kappa I in the beta weak sense, and then the kappa I are converging, these are just numbers, the kappa I, to some limiting number kappa, then this theorem is saying that if this situation holds, then it follows that this limiting metric g also has scalar curvature bounded below by kappa in the beta weak sense. Okay, so in other words, the limiting metric has scalar curvature bounded below by the limiting number. Oh, I think, is there another thing in the chat? Okay, yes, that's the prism one with cubes. Okay, thank you. Okay. Okay, and so, one thing that follows from this theorem is that we can answer this question by Gromov. And so the question is the following: let G be a continuous Riemannian metric on a closed manifold M, which admits a C0 approximation by smooth Riemannian metrics Gi, such that the scalar curvature of Gi is bounded below by negative epsilon I, where here this negative epsilon I goes to 0 as I goes to infinity. And the question is, does M admit a smooth metric of non-negative scalar curvature? And so we can see from this theorem that the answer to this question is certainly going to be yes, because G is going to have non-negative scalar curvature in the beta weak sense. And so any regularizing Ricci flow is going to have non-negative scalar curvature for all positive time slices. Moreover, after we push forward the regularizing Ricci flow by the appropriate family of diffeomorphisms, we will find a smooth family of metrics that have non-negative scalar curvature and that converge uniformly to G. Okay, so the answer to this question is yes. Moreover, G admits a uniform approximation by smooth metrics of non-negative scalar curvature. So anyway, I just mentioned that because somehow this is kind of a nice consequence of using Ricci flow to think about problems concerning lower scalar curvature bounds. I should just mention, if you don't like dealing with this beta weak definition, you can also prove this corollary directly just using the Ricci to Turk flow. And the proof of this corollary is the same, or more or less the same as the proof of this theorem. I think, let's see, there's another question in the chat. What does the existence time t of the flow depend on? Okay, so what I will do is if I have my C0 metric, I will choose some smooth background metric, which is very close to the C0 initial metric. And the time of existence is going to depend on the curvature of that smooth background metric. Other questions? Okay, no problem. All right. How are we doing on time? I have some time, so I think I will also mention the following result. Okay, so let me just remind you of this following theorem. This is the scalar torus rigidity theorem of Shane and Yao and Gromov and Lawson. And it says any Riemannian manifold with non-negative scalar curvature that is diffeomorphic to the torus is isometric to a flat torus. And so we can answer this question. This question was posed to me by Christina Sormani, and we can ask whether it is possible to prove sort of a C0 version of this theorem for C0 metrics that have non-negative scalar curvature in the beta weak sense. And so here is the answer to this question. So the question is, suppose G is the answer to the question is, suppose G is a C0 metric on the torus, and that there is some beta between 0 and 1/2 such that G has non-negative scalar curvature in the beta weak sense everywhere, then the torus with this metric G is isometric as a metric space to the flat metric on the torus. Okay, and so when I say isometric as a metric space, what I mean is that I can find a C0 bijection, which preserves, the distance function, but I don't know whether this bijection is actually going to be smooth, I don't know whether the bijection is going to be smooth with respect to the original smooth structure on the torus that I started with. Okay. And so, the way that you would show this is as follows. So because G has a non-negative scalar curvature in the beta weak sense, what I can do is I'll take a regularizing Ricci flow for G. And since I know uniform lower scalar curvature bounds are preserved under the regularizing Ricci flow, the scalar curvature of every time slice of the regularizing Ricci flow is going to be non-negative. And then since we're working on the torus, that means that this is going to be a flat constant flow. And so we have a flat constant flow that converges uniformly modulo push forward by diffeomorphisms to G. So that means that G is Gromov-Hausdorff equivalent to a flat metric on the torus. All right. Oddly, somehow this statement cannot be improved. And the reason for that is that the regularizing Ricci flow somehow cannot tell the difference between metric space isometries and Riemannian isometries. Okay, and so here is the proposition that makes that more precise. The regularizing Ricci flow is invariant under C0 isometries, i.e. if phi from M2 G2 to M1 G1 is a metric space isometry, then for any two regularizing Ricci flows tilde GT1, chi1 and tilde GT2 chi2 for G1 and G2 respectively, there is a stationary diffeomorphism alpha from M2 to M1 such that the pullback of tilde GT1 by alpha is equal to tilde GT2, and chi1 pre-composed with alpha is equal to, chi1 composed with alpha is equal to phi composed with chi2. Okay, so somehow, it's a bit odd, but you cannot use the regularizing Ricci flow to distinguish between smooth isometries and just metric space isometries. Okay, so anyway, I just wanted to mention that because somehow this illustrates this slightly odd property of the regularizing Ricci flow, which I had not expected. Okay, I think, are there any questions? Okay. So far what I have done is I've told you how to make this C0 definition of a pointwise lower scalar curvature bound using the regularizing Ricci flow. And I've sort of told you that it satisfies certain nice properties, and then I've explained some open questions. And now what I would like to do is I would like to explain a little bit about how to prove some of the results that I have mentioned so far. Okay. So the first result that I would like to explain how to prove is this result that asserts the existence of a regularizing Ricci flow. Okay. And so, in general, even in the case of smooth initial data, if you want to show the existence of a solution to the Ricci flow, one thing that you have to contend with is the fact that the Ricci flow equation is not strongly parabolic. And you would kind of like it to be strongly parabolic, then you would expect that you have a good chance of finding a nice smooth solution, but it's not strongly parabolic. And so what we do in order to solve the Ricci flow, this is an idea of de Turck, is we sort of first solve a related equation, which is strongly parabolic. This is called the Ricci de Turck equation. And then somehow, we're very lucky and we can pull back, once we have a solution to the related equation, we can pull back that solution by a family of diffeomorphisms to find a solution to the Ricci flow. Okay, and so that sort of accounts for the presence of these diffeomorphisms. And so as I mentioned earlier, really what this is saying is that you can find a solution to the Ricci de Turck flow that converges uniformly to the initial data. Okay, so to summarize, in order to show that there exists a regularizing Ricci flow, what we're first going to try to do is find a solution to the Ricci de Turck flow starting from C0 initial data. And then once we have that, we will be able to pull it back by a family of diffeomorphisms to get a regularizing Ricci flow. So sort of the hard thing is to find a solution to the Ricci de Turck flow. Okay. And yes, so this is the Ricci de Turck equation. I'll maybe make a little more precise some of the things that I just said. So this is the Ricci de Turck equation. And it turns out that, this equation does not actually look much easier to solve than the Ricci flow equation, but it turns out it is, a little bit easier to solve this equation than the Ricci flow equation. It's a bit nicer analytically. And then once we have a solution to this equation, we can pull it back by the family of diffeomorphisms generated by X. Oh, okay. Generated by this vector field X. This is some time-dependent vector field. And if we pull back a solution to this by the family of diffeomorphisms generated by X, it's not so hard to show that the result will be a solution to the Ricci flow. Okay. And so, right, so now what we need to establish is the existence of a Ricci de Turck flow, so the existence of a solution to this equation starting from C0 initial data. And this is a fairly well-studied problem, okay? And so I think the first results in this area are due to Miles-Simon in 2002, and then Koch and Lamb have some results on this from 2012 and 2015, and then I also looked into this a little bit. And the upshot of all of these results is that there exists a smooth short-time solution to the Ricci de Turck flow starting from C0 initial data, which converges uniformly to the initial data. Okay, and so now that we know that this solution to the Ricci de Turck flow exists, we can pull it back by this family of diffeomorphisms generated by this vector field X, and we can get a solution to the Ricci flow, and that solution is going to be our regularizing Ricci flow. Okay.
Oh, maybe I have a stupid question. Yeah, G is a C0 estimate, but the equation need to compute the Ricci. So the equation is not well defined at t equal to 0.
Correct. Yeah, so what this means is that you will have a solution that it satisfies this equation for all positive times, and it converges uniformly to G as t goes to 0.
Okay.
Yes. But yeah, thank you for the question. I didn't really explain that. Other questions? Okay, and so, this is how we establish that there exists a solution to the this is how we establish that there exists a regularizing Ricci flow is by first solving the Ricci de Turck equation and then pulling it back by these diffeomorphisms. So this was one of the results I wanted to explain to you. Another result I wanted to tell you about is how to show that my definition was stable under greater than second order perturbation of the metric. And in order to do that, I actually want to talk a little bit more about this method of Cohen-Lamb for showing that there exists a solution to the Ricci de Turck equation. And so I'll explain, why that is relevant in a second. Okay, and so basically, what Cohen-Lamb do is that they show that a solution to the Ricci de Turck flow arises as the fixed point of some kind of like integral operator, and then they come up with these norms. These are the norms, and that they show that with respect to certain conditions on the initial data, this integral operator is going to be a contraction mapping with respect to this norm, and so it's always going to have a fixed point, and therefore you will always have a solution to the Ricci de Turck flow. Okay, and so in the course of showing that this integral operator, which I will not mention, is a contraction mapping, they prove a result that looks kind of like this, or it doesn't look kind of like this, it looks like this. And so what this is saying is that if your initial data is close to some background metric, so here bar G is just some background metric, this is saying if your initial data is close to some background metric in C0, then your solution to the Ricci de Turck flow, that's what GT is, your solution to the Ricci de Turck flow will remain close to that background metric, with respect to this X norm. Okay, and so, the thing that is sort of relevant for us about the X norm is that it has this L infinity part. And so again, what this is saying is that you have initial data that is if you have initial data that starts out close to some background metric in C0, then it's the corresponding Ricci de Turck flow will stay close to the background metric, also in C0. Okay, and so the reason that is relevant to us is, okay, let me skip this, let me just remind you what I wanted to show is in order to show that the definition was stable under greater than second order perturbation of the metric, I wanted to show that if I have two initial metrics that agree to greater than second order, then their Ricci de Turck flows. So remember that these were the families of metrics that approximate the initial data. So these were the Ricci de Turck flows. Okay, so what I wanted to show was that if I have two initial metrics that agree to greater than second order, then their Ricci de Turck flows also agree to greater than second order. We can think of this statement as saying that they sort of continue to agree to greater than second order. Okay, and so the reason that this proposition of Cohen-Lamb looks sort of relevant to this result is that here, we have two things that are close initially, and then we show that they stay close in some sense. And again, here we have two metrics that are close initially, close in the sense that they agree to greater than second order, and we want to show that they stay close in the sense that their scalar curvatures stay close. Okay, and so somehow what we would like to do is use this approach of Cohen-Lamb, but sort of adopt it to this situation. All right, and so yes, so here again is the thing that we're trying to prove. And so, Cohen-Lamb had one piece of initial data that was close to some background metric. I have two pieces of initial data, okay? And then they wanted to show that their Ricci de Turck flow stayed close to the background metric, and I want to show that my Ricci de Turck flows stay close to one another. I don't know why I did that. And they had, their initial data was close in C0, but I actually have my two initial metrics are close not only in C0, but actually they agree to greater than second order. And so what I'm going to do is I'm going to put some weight onto here, such that this right-hand side is finite when G0 prime and G0 prime prime agree to greater than second order. So in other words, the fact that G0 prime and G0 prime prime initially agree to greater than second order means that their difference looks something like this. Okay, this is X naught. And so this weight that I put onto the expression here is basically going to be 1 divided by this picture. And so the fact that the two metrics initially agree to greater than second order means that this right-hand side is finite. Okay. And then I have to put something on the left-hand side. Now, what I want to show is that the scalar curvatures basically agree. And essentially what that boils down to is showing that the Ricci de Turck-Flows basically like more or less continue to agree to greater than second order around X naught. And so what I would like to do is also put some weight on here that shows that the two metrics like kind of continue to agree to greater than second order. Now, ideally I would like to put the same weight that I have here over here. However, if I have this, a picture that looks like this, and I evolve it by something parabolic like the heat equation, what I would expect is I would expect that this picture is going to draw in some heat from out here. And so in this region, it's going to raise up a little bit. And so the weight is actually going to have to get a little bit weaker. And so the amount that this region will sort of, I'm being very vague, but the amount that this will raise up is sort of like square root of t. Okay, and so it turns out that if you modify your weight and you sort of smuggle in a square root of t here, then the following expression is true. Okay, I think here I need t to the beta. And then this is, I have to pick up something finite, but that doesn't matter. Okay. And so sort of using this method of Cohen-Lamb and by putting weights on their norms, what we can conclude is that if you have two metrics that initially agree to greater than second order, then this weighted expression is going to be finite. And so that what that means is that the Ricci de Turck-Flows, continue to like more or less agree to greater than second order. Okay, and so once you have this weighted estimate, it's actually quite straightforward to prove this statement about the scalar curvatures. Okay, and so this is how we prove that this C0 definition is stable under greater than second order perturbation of the metric is by using this estimate of Cohen-Lamb for solutions to the Ricci de Turck-Flow that are initially close to some background metric, and then putting weights onto those norms, and somehow by weighting those norms we're able to obtain that the scalar curvatures of the Ricci de Turck-Flows for the two pieces of C0 initial data stay close. Other questions about this? Okay, so the last result, it looks like I'm going to end a little bit early, sorry about that. The last result that I wanted to talk about was this result that said that uniform lower scalar curvature bounds are preserved under the regularizing Ricci flow. Okay, so let me just remind you what this theorem said more precisely. So, we're assuming M is a closed manifold and G is a C0 metric on M. And suppose there is some beta such that the scalar curvature of this C0 metric G is bounded below by kappa naught in the beta weak sense everywhere in M. And so then the statement is, if tilde GT is a regularizing Ricci flow for G, then for all positive time slices for which the flow is defined, the scalar curvature of tilde GT is also bounded below by kappa naught. Okay, and since I'm going to be dealing rather explicitly with the definition in this proof, let me just remind you, this was the definition of the beta weak, not negative, or beta weak lower scalar curvature bound. Right, so yeah, so basically what we're going to do is suppose that this theorem is false, and then we will try to show that actually this condition could not have held at some point. Okay. All right. And so, yeah, so let's just argue in the case where kappa naught is equal to 0. Okay, so what I'm going to do is I'm going to suppose that this theorem is false. So actually we can find some positive time and some point on the manifold where the scalar curvature is bounded above away from 0. And then what I will do is I will, use the evolution equation for the scalar curvature under Ricci flow and use some heat kernel estimates to show that, well, if that were the case, then in fact there had to be a nearby point at an earlier time where the scalar curvature was also bounded above away from 0. And then, I can look at this nearby point and its earlier time, and show using the same method that actually there had to be another nearby point at an even earlier time where the scalar curvature was also bounded above away from 0. And so, doing this sort of iteratively, what I will do is I will construct a sequence of points that are all very close to one another and a sequence of times that all go to 0, such that at each of those points and the corresponding times, the scalar curvature is bounded above away from 0. And so in particular, there had to have been some point where this condition fails. Okay, so let me make that a little bit more precise. So let's suppose there exists some point x and some positive t, such that the scalar curvature of the regularizing Ricci flow at x at time t is bounded above by some negative epsilon, so bounded above away from 0. And then what I'm going to recall now is the fact that, sorry, I'm getting ahead of myself. And so what I would like to show next is that actually there's some point close to x such that at time t over 2, the scalar curvature is also bounded above away from 0. And so suppose that that is not true. So actually suppose that on the ball of radius x times, ball of radius t to the beta around x, the scalar curvature has a good lower bound. Okay, and I've put a blank space here because I'll have to pick up an error. Okay, so what are we supposing? We're supposing that we have some point at some positive time that has scalar curvature bounded above away from 0, but that at all earlier times nearby, the scalar curvature is not bounded above away from 0. It has a reasonable lower bound. Then what we will do is we will use the fact that under the Ricci flow, the scalar curvature is a super solution to the heat equation. So if we want to lower bound the scalar curvature at a later time, what we can do is integrate the scalar curvature at an earlier time against the heat equation. Okay, so let me make that precise. So, we're assuming that the scalar curvature at x at time t is bounded above by minus epsilon. And then, as I just said, the scalar curvature at x at time t is bounded below by integrating the scalar curvature at time t over 2 against a heat kernel based at x. Okay, so let's integrate the scalar curvature at time t over 2 against this heat kernel in the ball of radius t to the beta. And then we're also going to integrate the scalar curvature at time t over 2 outside the ball of radius t to the beta. Okay, so here we're integrating the scalar curvature at time t over 2 against a heat kernel over the whole manifold, but I've split it up. And yes, and so here we will see why it is significant that beta is less than 1/2. And so within the ball of radius t to the beta, we are assuming that we have a sort of reasonable lower bound on the scalar curvature. Okay, so we're assuming that the scalar curvature is bounded below by minus epsilon plus some error. Okay, so this is the same error. And sorry, this should be a strict inequality. And then outside the ball of radius t to the beta, the scalar curvature could potentially be very, very negative. Okay, but that doesn't really matter because outside the ball of radius t to the beta, the heat kernel is going to decay exponentially. And so even if the scalar curvature over here is like very horrible, this heat kernel is going to sort of, I don't know, cancel it out. Okay, and so, yeah, so even if the scalar curvature is very negative, this term is at worst this bad. All right, and so in order to get a contradiction, all I need is to pick up this error term. Okay, and so, observe that due to the fact that beta is strictly less than 1/2, this error term decays exponentially as t goes to 0. Sorry, I need to put the same error term here. Okay. Okay, so I have my contradiction. And so it follows from the contradiction that if there exists some point x and some positive time t such that the scalar curvature is bounded above away from 0, then actually at time t over 2, there had to be some point in the ball of radius t to the beta around x such that the scalar curvature was also bounded above away from 0. And now I could repeat this argument and go to time t over 2 and this new point and show that nearby this new point at time t over 4, there also had to have been a point where the scalar curvature was bounded above away from 0. So if I repeat this process, I'm going to come up with a sequence of points that are all of radius t to the beta away from each other. Such that at every, at every point and at every time sorry, I'm saying this so backwards. Okay, just to summarize, I can construct this sequence of points xk such that the scalar curvature at xk at t over 2 to the k at time t over 2 to the k is always bounded above away from 0. And then because these xk are always close to one another, there is some limiting point x infinity such that the xk all live in this ball around x infinity of radius c times t over 2 to the k to the beta. Okay, this looks complicated, but what follows from this statement is that this condition here could not have held at x infinity. Okay, and so that's the contradiction. Okay, so just to summarize, since I said that in a sort of convoluted way, just to summarize, the way to prove this is to suppose that it's false and then use heat kernel estimates to show that if the conclusion were false, then actually this beta weak condition could not have held everywhere. And basically the significance of this t to the beta is it's sort of the amount that these bad points are allowed to move apart. Okay, I think that was all I wanted to say. I can take questions now if there are questions.
Very good. Thank you, Paula. The talk was great. So we have plenty of time for questions, actually. Questions in the room?
Oh, there's a question.
In the chat.
Yeah. Yeah. So actually, I would like to ask the same question I already asked, but maybe you can say it more precisely now. So if you have a convergence, a C0 convergence of matrix to a fixed metric, then do you get uniform existence times for all your metrics?
Yes, because eventually all of those metrics should be close to the same background metric, and the existence time only depends on the background metric.
Okay. So there's something which is uniform, so which is independent of anything. So there's some constant, this C, which appears by you. So this only depends on the dimension. It does not depend on the background metric. Okay.
Yes, and it's because somehow I've like shoved all the dependencies into the time interval.
Thanks.
Mm-hmm.
Okay, there is a question asked by Christina on the chat.
Oh, more about the heat kernel estimates. Okay, so yeah, so the heat kernel estimates, let's see, what can I say? I guess, okay, so somehow these are like standard exponential heat kernel estimates. The difficulty with this proof is that, what do I want to say? Yeah, so the difficulty with this proof is that, here we have this, I guess, okay, for simplicity, let's work with the Ricci to Turk flow. So we have this smooth family of metrics that converges to something which is only C0 as t goes to 0. And typically with these heat kernel estimates, your constants depend on the curvature of the family of metrics, which is slightly problematic, because the curvature is going to blow up as t goes to 0. But somehow this is actually not a problem. And the reason it's not a problem is because we have this curvature bound for the flow that looks like this. But then we're only ever working on time intervals of size like t over 2 to t. And so somehow this makes it sort of like not so problematic that the curvature is blowing up as t goes to 0. But yeah, the heat kernel estimates, okay, I'm worried. I don't think I want to write one down because I'm worried I will get it wrong. But they're basically like estimates on the heat kernel in terms of like, some constants times the Gaussian, the like standard Euclidean heat kernel. Okay, so would something like this work for possibly singular initial data? I'm not sure. Yeah, so at least this construction of Koch and Lamb for the Ricci to Turk flow, I don't know. If you have initial data, which is just close in L infinity, you can still find a solution to the Ricci to Turk flow, but I don't think that it would converge uniformly to the initial data. I think it would probably only converge like almost everywhere to the initial data. And so certainly with this approach, I have concerns that it would like meaningfully give you a way of, I don't know, dealing with those singularities. Like somehow, I don't know, you would just get, it seems to me that maybe you would just get a Ricci to Turk flow that like does not have that much to do with this singular initial data. So yeah, I'm not so sure, but I think there are people who have worked on things like Ricci and Ricci to Turk flow for singular initial data. And so maybe you could use a slightly different approach. Yeah, but I'm not so sure.
More questions? Okay, so just let me mention that tomorrow, tomorrow for us, the talks will start a little bit earlier. So at 9:30 is the first talk, 9:30 a.m. I'm supposed to say Central European time, which usually I say Paris time. And I apologize for that. People in California might want to go to bed like 2 a.m., so it's possible to attend the first talk. And there is a little miracle. The first talk will be on a blackboard. I even don't remember how to use a blackboard, but hopefully it's going to work very well. Okay, so let me thank Paula for this very lively and just great talk.
Thank
and
you.
Maybe we'll see each other tomorrow. Thank you, Paula.
Thank you. Bye.
Bye.